Welcome back. The first speaker of the afternoon session will be Sabrina Pasterski, and Sabrina will tell us about swing surfaces in AdS CFT.
Okay, so thank you guys for giving me the opportunity to talk here. It's an awesome, I'm excited for this week, and especially excited that I get to give my talk on the first day so that I can just enjoy the rest of the talks through the week. So thank you, or whoever is responsible for that. Basically, as the title says, I'll be talking about swing surfaces in AdS CFT. And the motivation is, I guess, twofold. The first thing is that we want to understand let me make sure this is still the right view. Okay, it's fine. If it starts moving down, I'll be scared. We're going to basically be exploring a proposal for a holographic entanglement entropy in asymptotically flat spacetimes, hence the name swing surfaces. And part of the goal of this project with Jackie and Rob is to understand how to uplift this construction to AdS CFT and see what that tells us about either what these objects are or like any insight into why this proposal is working. And so the two papers that I'm going to be referring to quite a bit are these works by Miller and collaborators from 2014, and a series of papers that started with this one from 2017 by Wei-Sung and collaborators. And basically those two different references are looking at boundary and then bulk duals to this proposal for a flat space entanglement entropy. So let's see. This was good. Aligned back. Perfect. So roadmap for the talk, motivation, which is going to be also like, so why am I talking about this and what are swing surfaces? And then we're going to go through taking the flat limit of AdS CFT, lifting the proposal back up to AdS, and then close with some fun things in this nice short 30-minute talk. So let's go ahead. And I think for anybody at this conference, it's quite clear that we've learned a lot about the interrelationship between quantum information and quantum gravity in AdS CFT. And basically, like AdS CFT then becomes this playground where we get to play with bottom-up questions, like where various regions of the boundary theory are going to be encoded in the bulk. And so it would be lovely if we could take all of that framework and learn something about asymptotically flat spacetimes. So me as a celestial holographer and or just flat holographer with some nice branding, I want to understand how I can do cool things with my asymptotically flat spacetimes, and I don't know how to do that stuff yet. So what do we have at our disposal? If I am sticking to 3 dimensions, there's actually quite a lot of literature where people have both studied, I guess, like flat limits of AdS and this whole BMS symmetry in my asymptotically flat geometries on the right-hand side. And then also there's been a lot of literature on Carolean CFTs in particular, 2D BMS field theories, precisely for the same reason that 2D field theories are, with conformal symmetry, are more interesting in the usual case. And so basically, just from the point of view of staring at the conformal diagram, it might make sense that if we were looking at a natural dual description, I have some sort of scattering process in my asymptotically flat spacetimes. That data is going to go out to null infinity. My codimension 1 boundary that at least I see in this Penrose diagram is going to be null. And so already that hints at the theory being kind of a strange type of field theory, this ultra-relativistic Carolean theory. And so we're trying to play with some aspect of this duality that people have understood. And that's in the context of an entanglement entropy. So I want to point out that, as a warning, I'm talking about 3D bulks throughout this talk. And so in particular, a lot of the constructions I'm talking about, I am really basing it at like geodesics from ART surfaces or whatnot. So let that warning be clear. Okay. So before I get into, I guess, more of like the equations and derivations, I want to talk about what the swing proposal is. So what's the title of the talk? The first claim is that someone hands you an entanglement entropy in a BMS field theory. And so this is supposedly some Carolean theory where the central charges are fixed by this flat limit that we'll talk about in a few slides later. But say Miller and collaborators, or Arden Bagchi and Miller and collaborators, hand me this equation for supposedly an entanglement entropy for some region of my Carolean theory at null infinity. And then what happened is someone came along, and Wei-Sung and friends found that that same quantity in this case of, say, for example, just Einstein gravity in the bulk, we can even restrict to just asymptotically, like just actually Minkowski space and not more interesting examples, they can find a bulk, I guess, geodesic segment that has the same length as we would expect for the usual like area over 4G from this proposal. So the way that the swing proposal is defined is quite strange. It's not like the usual RT proposal. And so what the name of the game is the following. So I'm interested in some interval on null infinity. And so, right, because I'm in 2D boundary, I have just one phi direction and then a u time direction. That's null. I take where my interval was. I shoot in radial geodesics. And when I have those null geodesics, I then look for some other geodesic segment that is spanning between the two. And then I extremize over where those, that geodesic ends on the two null ropes. And if I try to find that saddle, I'll find a unique one in the case of this flat space-time single interval example. And the length of that guy matches this BMS field theory entanglement entropy for right-side gravity in the bulk. And so that's a neat observation. It's a very strange version of the proposal. And then the point of the talk today is try to unpack that, uplift this construction up to AdS, see how weird it is, what is this quantity in the boundary theory and then the bulk theory, and then list some fun things we've been playing with since then. So maybe any questions at that level right now before I go into it? Good. Okay, awesome. So now we're going to just go about adding more of the details to the various constants appearing in those equations and see how we went about getting the flat limit result. And then we'll have more fun later with interpreting what it is in AdS CFT. Great. So we get to have fun as follows. We're going to start being in global AdS. And in that case, it's straight enough to see like how I get to my asymptotically flat spacetime, in this case just Minkowski space, because I want to just stick to the specific case of global AdS right now. And so what I can do is the first thing I might want to do is do a coordinate transformation so that I have kind of a nice flat limit to my retarded coordinate u on the boundary. And so that redefinition of time in terms of u and now this AdS scale dependent quantity of like radius turns me into the metric in the second line. And then I can clearly see that now if I want to take a flat limit, I'm going to land on my flat space-time. And then the one thing to point out, because in these games I keep talking about Carolean theories in the boundary or whatnot, is if I, instead of taking the flat limit first, took the large R limit first, and then I strip out my conformal factor, I see that indeed I have that time-dependent part of the metric, have this 1 over the AdS scale. And so we see that taking the large radius limit is like basically sending my speed of light to 0. So that is the sense in which we can literally see from this AdS flat limit that my flat limit is taking a Carolean limit of the region of the boundary that's mapping to my null infinity. Great. Good. And so again, pointing out what's happening, if I'm zooming into that little band and kind of like stretching things out, it's the same procedure of seeing my light cone basically crunch up to being just the generator that I'm along. And so I have now this kind of ultra-local theory at null infinity that is this Carolean field theory that would be wherever like massless excitations would exit on scry. And I want to point out too that in a lot of these equations, because I'm going to be kind of starting to mix various convections later, I want to keep the most general case in mind where I can have a different left and right moving central charges in the AdS context. And that's in topologically massive gravity that I get to now have a C plus and C minus that are different. And what we find then is that we can have non-zero central extensions for both the super rotations and the super translations in that case. So what I'm doing in this slide is I'm just saying I have my Virasoro symmetry with 2 separate central charges in the most general case of topologically massive gravity in AdS. I can form some linear combinations where in that same story of where I'm taking that flat limit and zooming into those little bands in the cylinder, I now have my theory, say, at null infinity with a representation of BMS that is centrally extended, with the central extensions being related to the TMG terms. And in particular, we see that that AdS scale has stripped off from that flat limit. And so at the expense of this central charge for the translation and super rotation generators now having some dimension, I don't have any AdS scale in this problem. So I have a BMS symmetry. I get that from a flat limit. I can also take a flat limit of the geometries in the AdS. and have my asymptotically flat spacetimes. But the place where things start to go funny when people are now using this to talk about entanglement entropies, nominally from a very just boundary field theoretic point of view, is the fact that the representations that I'm interested in are a bit different because of this flipped modding. And so you can imagine that, well, just for later, there will be the dragons. Okay, so again, from this point of view, I now take a flat limit of AdS, and I'm zooming into that little kind of time band that's that pi over 2 plus something of order 1 over L. And then I have now the stretch thing where, again, my causal domains of dependence are just now this band of null infinity because my light cones are just going straight up. And so one might think just at this stage, if I am trying to talk about entanglement entropies in this Carolian theory, it's ultra-local. Maybe I should be worried about a different entanglement structure. And so a priori, the fact that somebody handed me a very strange-looking quantity for the entanglement entropy, I am less scared because it's weird already. So maybe I need to think twice. So now that we have control over the kinematics of the flat limit, we're going to try to then talk about the swing proposal itself in the context of knowing how we could have zoomed in and out. If there's a question in the back, I don't mind taking it now.
So just one naive question was, what is mu again?
So mu is this term in the TMG action. So it's setting the parameter for this Chern-Simons term. So if I send mu to infinity, I kill it.
Okay. And then, so do I think of this as having a central charge which is not 0, or because obviously naively, if I take the Brown-Hornell formula and I send L to infinity, then I kind of think that it would look infinite.
Infinite, yeah.
Sorry?
Yeah, so in that case, it would look infinite, not 0, right?
Right. Okay. So what's the kind of correct answer for this particular model?
Yeah, so I think again, this will trace back to, and we'll see it kind of at the level of comparing the RT formula later too, but it's really tracing back to these dragons in the sense that basically by taking that combination, you are having the translations be the ones that I guess have the non-zero, so what I'm saying is, depending on the type of contraction I do, there's this ultra-relativistic one that's relevant for this Carolian theory. We're taking this limit. There's one where I could flip time and space, and that would roughly change the plus or minus signs in the L's versus the M's. And because I have, when I take that translation generator, I'm contracting doing a 1 over L. That's where it removes that AdS scale. So these central charges are finite as long as, say, mu didn't scale with L, in the flat limit. Okay. So BMS has a finite central extension.
Okay, thank you.
Yeah. Great. Any other questions? Good. Okay, so now we're going to have fun unpacking and kind of tearing and playing with this swing proposal for our asymptotically flat spacetimes in the context of now we want to lift up to AdS. So looking back to the slide before where I talk about this BMS field theory entanglement entropy, let's kind of stare at it a little bit about how different it is from the RT surface. So already I was pointing out that it's not this geodesic that just goes to, say, 2 points on my conformal boundary at AdS, say. But I also can stare at the behavior here and see a few kind of weird things. The first thing would be, so now that we understand the flat limit I took, I understand why I'm setting CL to 0. I want Einstein gravity in the bulk. Cm now is finite, so that's nice, but my entanglement entropy would roughly be 0 if I was on an equal time slice. So that's weird. It's not going to look normal. And indeed, if we just naively take the exact same prescription and lift myself back up to my global AdS spacetime for the simplest example, then I could see that, sure, I can send in my radial geodesics. I can do that as long as I have some notion of, say, the angular momentum symmetry to, align the way that I'm picking those geodesics. I can find the swing surface, and in the flat limit, it would again match to the answer from before. But it's now very different from the AdS RT surface that we would think should correspond to if I thought of that cut of null infinity as being some cut of my AdS cylinder in that time band near pi over 2. And again, that entanglement entropy then should be that RT surface, right, from what we would know from AdS CFT. So this guy is quite different. So we want to just have fun with that. These next few slides don't probably need too much mention given the audience, but I do want to point out a couple of equations that we're going to refer back to when we try to explain what's kind of weird about this entanglement entropy proposal. And so, of course, if I was just an AdS and say I'm looking at a constant time slice, I can cut off my space-time, measure length of geodesic, and I reproduce what I expect from RT. And then the thing to point out is that kind of the mechanism by which I would match it from running entropies in the boundary theory, I have these twist operators with some fixed dimensions that I can match to from my stress tensor correlators on this multi-sheeted geometry. And so later we're going to try to unpack why when they were doing the exact same games, they landed on this different answer. The other thing that I want to point out is, again, the answer that I would get if I was in TMG for the purposes of isolating the left and the right moving terms that otherwise I would just more naturally combine into the function that only depends on, say, delta phi. And so in particular, for the t equals 0 case, in particular, I'm going to want to come back to that equation when I stare at what is this difference between the BMS field theory entanglement entropy and the usual entropy. So where did the BMS field theory entanglement entropy come from? It basically, again, came from the representations we were assuming the states were in. And so if you track through these papers where they're first proposing this quantity, what they're doing is they're using kind of the fact that they wish that they had BMS primaries in the sense that you have this algebra, you have no L dependence in it, you want to find some good representations of this BMS. They are able to find what the entanglement entropy would be if I could just take my primaries under Virasoro for my twist operators and take a limit where I would have them still be BMS primaries. They get an answer for the entanglement entropy only in terms of the central charges, and then they swap them back out for the central charges that you'd have in flat space. And so that sounds a bit mucky, and it is because you're roughly trying to just take advantage of some automorphism where it's not really an automorphism because I need to swap out the sign of the, say, left-moving central charges. But that's basically the kind of mechanism underlying how they ended up getting to this answer. And so you can see if you stare at the formula for the BMS field theory entanglement entropy, because I'm in a bulk theory with C plus equal to C minus, I have 0 CL, I get this swing proposal here. And you're basically getting that answer because you went through the circuitous route trying to use the fact that the answer should only depend on the central charges of your theory. And you end up effectively saying that your twist operators are primaries with certain weights under the BMS algebra. But if I had instead asked what would I actually have expected if I put a twist operator out at this u equals 0 cut, I wouldn't be getting that. And so in particular, the states that I have that are the usual Virasoro primaries in my cylinder, which I still want to think of when I'm taking that flat limit, that's a different, I guess, BMS subalgebra than you might naturally get to if you tried to conjugate and move those generators up to this u equals 0 cut. And so in particular, this whole funny business is in whether or not I have something that's highest weight versus lowest weight under the L bars. And so that's like inverting my Z bar coordinate. And on the cylinder, it's like flipping my time and my space. And so there's this notion of ultra-relativistic versus non-relativistic computations you can do in this dual theory and try to land on answers. And so there's some funny games there. But in the end, basically what's happening is that if I had decided to put my twist operators instead, like moving them from the origin out to that band, I would be conjugating with some global symmetry of AdS that has an AdS scale dependence in it, so it's not a nice Poincare symmetry. And so when I do that, when I take the flat limit, the linear combinations I have don't have to be the same ones that had a nice flat limit before. And so in particular, there's some other BMS subalgebra which has a divergent central charge that would not have this mixing of the modding. So I would have the L ends and the L bar ends in those combinations. And so what that mechanically does for us is it kind of explains how some things would work. To the extent of Hijano and collaborators were able to kind of use the BMS field theory and these like highest weight representations to kind of bootstrap the form of the conformal blocks. So it works because there is another BMS subalgebra that I would have acting on the operators near null infinity, and they take that flat limit. But in that one, the weights of the twist operators are quite different. Sorry about the pixelization there. And basically what I'd get instead is this divergent central charge, and I'd get back the answer that I'm used to, which in the flat limit is just depending on the angle. And so that, I probably should have changed the superscript on the left-hand side, but that's the mechanism by which you're getting this funny answer. And so fine. At that level, you can be agnostic enough, or whatever you want to say, and be like, someone might have flipped a sign somewhere. I have this quantity. It wasn't the entanglement entropy. I could be scared that the entanglement entropy that I want seems to be infinite. How would I actually compute that in my BMS field theory where there's no regulator there? Like, I'm not taking a flat limit, I'm actually just in the BMS field theory. And so we're trying to be a little bit more pragmatic about what we can do with it by just trying to see what quantities or how can we interpret this answer. Again, motivated more by the fact that there is also this bulk dual. So the fact that you have some proposal for an entanglement entropy in the boundary theory and a bulk object that matched it, is there something like that structure that I can lift up, even if it doesn't have an entanglement entropy interpretation in the AdS story. And so the first observation that we want to make is, again, due to this flip, effectively, of one of the central charges, the quantity that they're actually like handing you is roughly taking the flat limit of a difference between the left and the right moving entanglement entropies. And so one can also just compare that with a swing bench where there's an absolute value because it literally is like this distance, this length of that geodesic. And so that is just a true statement now for, say, a single interval in AdS, and we want to play with it a little bit more. And so before I then get to this fun kind of discussion session of throwing out different things that we've been playing with, basically, I think the main questions to think of is we want to understand, what is this BMS field theory entanglement entropy, in quotes? What's the mechanism by which it matches the swing bench? And then also what we can learn possibly from these flat space computations, if they would tell us anything fun from the AdS perspective once we could answer those first two questions. And I guess I'm going to like land or like stick to some examples that are maybe simple enough that I can make some concrete statements about what these guys are. But again, understanding the generalizations are going to be more important, so you can hold me to that in the questions. Great. So last section. So the first thing that I want to point out is that this BMS field theory entanglement entropy amounted to us flipping the relative sign between the left and the right moving contributions. And so in particular, I want to use the word modular flow with scare quotes, I should add, because I don't necessarily want to think of the space like modular flow as like literally like from my density matrix. But we'll see later the extent to which it is a space like vector field with some nice boundary conditions. And basically, if I just flip that sign between the left and right moving vector fields, I get the space-like vector field that was also used in the derivation of the swing surfaces I'll get to soon. And so if I'm in the context of a very simple single interval in global AdS, then I can have a few tricks up my sleeve to try to massage that quantity into something that I can recognize. And so in particular, there's a set of very boosted intervals where I can identify that difference as a mutual formation, somewhat by the accident of the fact that what I really had started with was a difference between the left and right entropies there, and then I have some nice features of this pure state where I can basically add the kind of holomorphic and anti-holomorphic complements, and then I can see that the difference would be expressed as a mutual information. And so it should be just a true statement that in the context of this single interval, I can interpret this BMS field theory as measuring this mutual information of this kind of null zigzag thing. Now, on its own, fine observation. The reason we came about it is something probably not worth going too much in this talk, but it is kind of cute that there's a very collinear limit of a 2-to-2 scattering process where I can think of those different tilted intervals as some decision regions for, like, say, boundary-only scattering. And that leads to literally identifying of, okay, the swing surface that someone was talking about would straight up be a quantity that you kind of are playing with in these focusing proofs. And so that led to why, like, okay, this is mutual information, but what is it? Fine. The more important thing for, I guess, unpacking like the physics of what it would be is trying to see why does this swing proposal match. So why did Wei Sung and collaborators go about saying that they thought that this radial geodesic prescription was the right thing? And so what it turns out is that they're trying to basically take an analog of this Cassini-Herta-Meyer story, where you're trying to do some maps from some domain of dependence to something that's topologically a black hole, and then in that map understand how to relate the entanglement entropy to that thermal entropy. And so what they're doing is basically trying to extend that CHM map beyond the outer horizon to the inner horizon. And so essentially with some then cutoff dependence, they're roughly probing some segment of the inner horizon of that black hole and then saying that that's equal to the entanglement entropy under their story. And so that's the game that they're playing. And maybe another reason why, like within the space of people exploring asymptotically flat spacetimes, dual to BMS field theories, entanglement entropies aside, there's also a result by Arjun and friends about thermal entropies. And there they are supposedly doing some Carty derivation for this BMS field theory and for this flat space cosmology. They are able to match the flat limit of the inner horizon area. And so they successfully reproduce this entropy from something that looks like Carty only in this flat limit. And so that is a kind of another motivation, even though in this case it's not this topological black hole, but like the quantity that is the thing you're kind of mapping to in the end, and that's Cassini-Hortemeyer's story, generalized, is something that also has a thermal entropy that they've successfully computed. So why does that work, or why is that interesting, possibly, is another related question, again, because of this map with these null segments pushing me kind of further into the bulk than I normally would go. And so kind of as a fun aside, you can see that basically if I started with the original Carty derivation, and I was very naive and just kept all the saddles that I get when I try to, if I do my modular transformation, I get this exponential, I want to find where do I actually have a saddle point in tau. Normally, of course, you just keep the leading saddle, but if you kept the various subleading saddles that you get from that quadratic equation, you would find that there's a subleading term that would match the difference between the left and right moving terms when I have the left and right moving taus be independent. And indeed, kind of ironically enough, that subleading saddle is the one that was isolated. If I take some flat limit first of that exponent, I would only find that subleading saddle. And so that's the mechanism by which these people who are like accidentally, I guess, just setting the flat limit end up finding a subleading saddle in the original story, which would capture the vector fields corresponding to the inner horizon, which is kind of fun. And then as one more kind of advertisement before I start closing off, basically, another thing that you could try to probe is that you can, like there's this story from Hijano where you're able to basically say these bulk operators corresponding to these radial operators supported on a radial ray are reproducing these BMS field theory correlators. Why is that? It's roughly because they need to be highly spinning in this different automorphism that I was talking about, or like a change of frame from the origin of the plane to my u equals 0 cut. And so I could try from symmetries to say that that should be some linear combination of light ray operators in the CFT. And so you might try to guess, like, okay, whether or not I want to interpret it now as a light transform of twist operators, maybe not. But at least I can try to see if these operators would be probing, again, like sub AdS scale physics or some interesting stuff with these swing surfaces. So I think there's fun directions to go there from the boundary side, too. And so I'll just close with some takeaways and next steps, which are roughly, how do I go beyond very simple examples like the single interval, want to generalize the story to higher D. I think the more interesting physics was like these other geometric probes of entanglement that would be relevant to scattering, in particular sub AdS scale physics from our boundary dual. And then questions of inner horizon thermodynamics being related to the story. If we don't think the inner horizon is something we should like have nicely from an AdS CFT, what does that say for some of these games people are playing for the BMS field theories in flat? So thank you guys so much.
Thank you, Sabrina. Now we have time for a few questions. Rana, do you have a question?
Yeah, so I'm intrigued by this match to inner horizon because we expect inner horizons to be unstable.
Yeah.
So is this relevant at all? Like, wouldn't quantum fields behave weirdly under this limit where you're zooming into the inner horizon?
So that's the thing that I wish to just understand like how the answers match. So like the kind of funny thing that I'm doing is that I'm roughly taking like a difference between left and right moving terms and think that I can get the inner horizon quantity. So I don't know if it's that I want to be able to actually see the inner horizon, which I would seem to physically need to if I'm probing it with these null guys. But if I had some prescription just in the boundary theory where I could match just getting R minus for some reason, that might be fun. So I would love to understand better, first of all, why the inner horizon is so sick. Like Nada's told me a little bit about it at lunch, what that means for what people are doing for the swing proposal.
Okay.
But at the same time, I feel like there's some hint at what I would want to do to try to pretend to get like at least the quantity R minus from the boundary theory by taking differences of left and right terms.
Any other questions for Sabrina? I have a question. Sorry, Pedro. Sure.
Can you just comment a little bit more on the light rays a bit slower?
Yeah.
That part was too fast. Yeah. Where are the light rays in A? Is A null? This A
Okay,
segment?
sorry. So basically, what I was just trying to advertise in upcoming, like I'm going to split the paper in two and not have it be this part. So I wanted to basically just say that for here, I'm interested in the kind of the other, sorry. So in this case, I'm taking the interval A and I'm shooting radial ones in. That's the prescription right now. Now, in principle, there's a full like horizons worth, or like, sorry, a whole light cones worth of which directions I could have picked. And so when we're setting up this dictionary of what a bulk light operator is, we want to keep track of X, some impact parameter there. But basically, from the prescription of literally what would be the entanglement entropy, it's the radial ones from that proposal. But the operators I'd be interested in should be some other linear combination that would have the ability to pick which angular momentum you say had for that.
Okay. So that segment there on top is not null, that between O1 and O2.
Between O1 and O2 is not null. The two guys going in are null, and to match the swing, they're specifically the radial ones. But the operator dictionary should roughly be some other linear combination that depends on like the impact parameter.
Okay. Can I ask another question?
Yeah.
So is it true that, did I understand correctly, that in the CFT there was something about taking the right modes and flipping them, treating the...
Sure, yeah.
Is there a physical interpretation of what that means on the CFT, forgetting about the bulk?
So the thing that I'm scared of is that I don't know that I would say that that's the physical thing I want to do right in the end. So I do not think that the way that they flip all of the, like, say, right-moving modes is something that I had a nice understanding of. I think that some people who do like null strings have played with it, but in that case, it's like they're gauging away the Virasor. So I don't know. Like, I've tried to find other references where they play these games, and I don't think there was one that was immediately applicable to explaining the like answer that Grumeller and friends had. But because I was,
But there was a paper that did that, but it was in the context of the scattering equations to try to project out the massive modes and to get just but it's a different game, probably.
Because is this a null string story, or is this something different, like a?
Maybe it's by Warren Siegel and collaborators. Yeah.
I'm not sure. I didn't find a reference where it's literally the opposite modding of the other movies. I guess Shibayashi states are a bit.
I was wondering if it had to do with working with different reality conditions, like changing the notion of Hermitian conjugate.
So in this context, I still, like, what scares me is that, like, I could even imagine, like, going through the story and using that automorphism and swapping, like, the central charge on having a very chiral theory and matching things. Like, I still think it's just a mistake to do that unless I want to try to find a reason for this thing to be the entanglement entropy. So I think I've latched too much onto that conclusion to have thought recently about this, but.
Okay, in view of time, let's thank Sabrina again.